Let's have a look at some of the key features of the graph of y equals e to the power of x. Now we know that it goes up very sharply. I probably haven't even drawn it sharp enough here, but these are the key features that you need to put on your graph. You need to draw it with an asymptote, so you can put that in as a dotted line, and the asymptote goes straight along the x-axis. We know that it has a y-intercept here at 1, and it has this basic shape. Okay. Now, anytime you are drawing any graph, really, you need to always put in things like asymptotes and intercepts, but it helps to have another point there also for scale. So at the moment, I've only got 1 point. I need at least one more. So pick any point, something nice and simple. I would like to say sub in something like x equals 1 into the equation because it's so easy. If I sub 1 in there, then y would be equal to e to the power of 1, which is just e. So I can put another point in here and say that when x is 1, y is e. And that gives me something of some scale on my graph. Now, key points of the graph. It only has one intercept. It has a y-intercept at 1. The domain, what values of x are possible? Well, we can have all real values of x because it continues in both directions. I should have an arrow down here. The range, what possible values of y are they? Well, anything from 0 upwards. But this asymptote means that y can't actually be 0. So y must be greater than 0. We have an asymptote on the x-axis, which is the line y equals 0. The basic shape, it's concave upwards. And that means that it's increasing at an increasing rate. Now let's think, what happens to x as x approaches negative infinity? In other words, as we go this way, what happens to y? Well, it gets smaller and smaller, it gets closer and closer to the x-axis, but it never actually touches it. So we could say y approaches 0. And what happens to the gradient? The further down this way we go, it gets flatter and flatter, doesn't it? So we could say also that dy dx approaches 0 because it's getting closer to a horizontal gradient. As x approaches infinity, going up this way, we could say that y also approaches infinity, even though it seems a little counterproductive because it's going up so sharply. It's hard to imagine it can ever get to those really large values of x, but infinity is, by definition, as big as it can get, so this holds true. And what would we say about the gradient as that graph continues up and up and up? Well, it's never going to be fully vertical, but it's going to get ridiculously steep, isn't it? So the gradient is also going to tend towards infinity. It's going to become a bigger and bigger and bigger number, and steeper and steeper and steeper. Now, what is the gradient at the y-intercept? Well, we've already learned that when we differentiate y equals e to the power of x, we get e to the power of x. So at the y-intercept here, we find that x is 0, isn't it? And if we sub in x is 0 there, anything to the power of 0 is 1. So not only is the height above the x-axis 1, the gradient will also be 1. So what we could do here is actually put in a tangent to the curve right at that point. We know that the gradient of this line is 1. We also know it goes through 1, so we could actually label that as a straight line, y equals x plus 1. And the gradient at the y-intercept is 1. That's one of the really notable things about this graph. We also know that the gradient at any value of x will actually just be e to the power of whatever x value you have. So if we're looking at the gradient, say here, where the x value is 1, e to the power of 1 is e, this height is e, but also the gradient would be e, around about 2.7 or so. And that will hold true for every value of x.